Perfect. All right, so as per usual, someone remind me, what was the very last thing we did? Yeah, we talked about our little squeeze slash sandwiching theorem, which stated that if I have an inequality, a compound inequality, where I have a function and it's bounded above and below by some other function, I can go ahead and try to find the limit of the top and the bottom. If it turns out that the limit of my upper bound and the limit of my lower bound are the same, then I actually know the limit of my middle function. It is quite literally squeezed in or sandwiched between two other functions. Other things we've done in the past couple of days, again, are how do you find a limit if I give you the graph, and how do you find the limit if I give you the equation or the function expression. So now we're going to go ahead and take a couple of steps back as a reminder to what we did on our second day. Let's go back to seeing what happens whenever I take a look at a graph, the graph of a function. So whenever I introduced a function, I may have informally called it the two-handed function or two-sided function. So we looked from the left and from the right. But the existence of a two-sided limit implies that there should be the existence of a one-sided limit. Not just the both ways, but the left and the right. So that's what we're going to look at today. What happens whenever I look at my one-sided limit? Instead of looking at both the left and the right, what if I only care about the left only? What about the right only? So let's look at this. For our first definition, suppose that I have a function f of x, or suppose f is defined for all x less than, let's do c this time. So I have a function and I have some sort of benchmark, and I want to make sure that my function is defined for all, and I guess I should be exact here, not just all. Let's do this, for all x near c. So I want it to be smaller than c, but also close enough. So for example, if my c is, I don't know, 5, I want to start thinking about the x values 4.5, 4.9, 4.99. I want to think about numbers that are relatively close to it. So suppose I have this function, and if we have that f of x is arbitrarily close, arbitrarily close to some value L. So I looked at my y value, we're arbitrarily close to L. Again, for all x less than c, sufficiently close. To c. So if I have that my y value is arbitrarily, my function arbitrarily approaches L whenever x gets closer to c, then we write the following. We write, let's see if I can fit right here. I'm going to zoom out a touch. And I'm going to write the notation first. So before I actually explain this notation, what is one key difference in the notation I see here that's different from before whenever we just talked about the limit? The key difference we're seeing here is that I see this superscript of a minus sign. And the way I'm going to read this is that the limit of my function f of x as x approaches c from the left is L. So we write this notation and call it the left hand limit. Call it the left hand or left side, whatever your preference is. Keyword here is left limit. So if you see this minus superscript, then this means that we're working to the left of C. Again, whenever we had our regular limit, we looked to the left and the right. This time, we're looking only on the left. So based off of this, can you take a guess what the notation for the right-hand limit is probably going to be? It's going to look like the exact same thing, but with a plus sign. So I'm not going to bother writing this entire paragraph again, but as a small note, maybe I should put it down here. If you ever see me use a minus sign, that's for the left. If you see me use the limit as x approaches c with a plus sign, this is for the right. The reason I didn't write this whole definition again is the wording is almost exactly the same. Like this, instead of working to the left, I'm working to the right. Oh, this right here, the definition is the left-hand limit. I should put this in a different color. So if you see the minus, it's left hand, plus is the right hand limit. Quick way that a lot of students remember it is if you think of numbers, we usually think of negative numbers on the left, positive numbers on the right, whenever you naturally think of the number line. In my other calculus class, they said that the way that they remember this is for the left-hand limit, they said it's like you're coming from the negative end of your number line, so the left. And then the same thing, the positive is like you're coming in from the positive side of your number line. So this is our definition that we're starting off with for today. And I'll give everyone some time to copy it down as needed. So whenever we introduced the two-handed limit last time, we start off with what if I have a picture, where do I work from there? So that's exactly what we're going to do here. I introduced the definition. Let's go ahead and do an example. So example 9. Let's evaluate these limits that I'm about to write if I give you this graph. So to just make sure that we're not moving too fast, I'll give you some time to copy the graph down, and then I'll actually write the problem itself. It looks like here we have sort of a linear function. Oh, and there's a small mistake I need to fix here. I guess it didn't register. There should be a filled in circle on top. So it looks like I just sort of have this combination of linear functions. In other words, a combination of lines I've drawn here. So I'm going to go ahead and ask for 6 expressions. I'm going to go ahead and write down parts A, B, and C first. Starting off with the limit as x approaches 1 from the left. The limit as x approaches 1 from the right. And the regular limit as x approaches 1 of my function. I do have a D, E, F portion that I'll hold off from writing. All right, so what x value am I interested in for parts A, B, and C? 1. I'm interested in what's happening whenever I'm close to x equal to 1. So just like before, I'm going to go ahead and just sort of draw this guideline at x equal to 1. Again, you don't necessarily have to draw this, but it does help in our visualization. So part A is asking for the limit as x approaches 1 from the left. So remember what I said in the previous lecture. Whenever I draw this line, it naturally divides my graph into two parts, the left side and the right side. So if I'm working with the left-hand limit, naturally we want to work with the left half. In other words, for part A, I'm not even bothering with looking on the right. I only care about the left. All right, so great. We have that so far. So if I want to work from the left, I start from the left of my line, and then I just want to follow my graph and get closer. So let's follow my graph. What y value does it look like I'm approaching from the left? 2. Again, my arrow is quite literally pointing, well not exactly, but pointing to 2. So my left-hand limit is a nice 2. I'm done with part A. Again, no calculations, we're observing the graph. What's going to happen for part B? The limit as x approaches 1 from the right. Well, let's go ahead and see. First off, am I working with the left side or the right side of the graph? Right. So let's just start on the far right and just follow my graph until I get close to my blue line. So if I follow it, I go here, and then I jump, and I follow it. Where does it look like I'm going or heading towards? What height? 2. So my right-hand limit is also 2. One small note I want to make. Was it really necessary for me to start all the way here on the right, or could I just start it here? It didn't really matter, because remember what our definition of a limit does. We're just looking whenever we're sufficiently close to x. This is really far. I didn't really have to start here. I could have just started here because I said this is definitely closer. But it is a good practice to just, one rule covers all, start all the way on the left, all the way on the right. All right, so we're done with part B. We looked on the left for part A, from the right for part B. What do you think is going to happen for part C? The limit as x approaches 1 of my function. Yeah, so remember, for part C, I'm looking from the left and the right. Is there a number that both the left and the right are approaching? And what happens to be that number? 2. And this should have been something very straightforward for us because, again, part C is a two-handed limit, the left and the right. Well, the left and the right were both going to 2. Therefore, the two-handed must also go to 2. So this is really great. All of my answers were 2. They all matched. However, this will not always happen. Let's go to part D, E, and F. For a second, I forgot what came after C. So I'm just going to move this aside to the left because I do want to keep it on the board whenever I zoom out. So D, E, F. Let's do the limit as x approaches 4 from the left, right, and two-sided. So from the left, from the right. And then our regular plain two-sided limit. So let's see what we can do here. And I'm going to go ahead and erase this, these old blue lines I had. Trying to keep my graph so I don't erase anything. All right, so once again, what x value am I focusing this time on? 4. So let's draw our sort of imaginary guideline at 4. So without me drawing the visual representation, what do y'all think my left-hand limit, well, the limit as I approach x as I approach 4 from the left is? 5. So left-hand limit, I only care about the left. I follow my graph and get closer to this middle line, and I see that I'm approaching a height of 5. What about the right? Yeah, I pretty much do the exact same thing, but from the right. Right-hand limit, start on the right, and I get closer to my guideline. Where am I heading? It looks like a 3. Now the question is, the one that we're interested in is, what about the regular two-handed limit? It does not exist. Why so? I heard a lot of answers, all correct. They don't meet each other. They're not the same. Because remember, again, the two-handed limit is saying I want the left and right to meet together. Clearly, the left and the right side, they went to different numbers. Therefore, we say does not exist. All right, so we have this here. Now I want to go ahead and zoom out. Well, before I do that, any questions about how I went through this example? I'm going to move this here to fix that P. There we go. So it didn't really matter as long as I get sufficiently close. You could have started here. You could have started here. As long as I'm just following my line and getting closer. This is also why this definition, like I mentioned from the second day, isn't that great. Because what does it mean to be close enough, sufficiently close? Generally for us, we're not going to be too worried about the exact wording of that, as long as we're getting closer. So I'm going to say that there's a pattern happening here. The question I want to ask is there a relationship between the one-sided limits and the two-sided limit? So if I look at, is there a relationship between A, B to C? And is there a relationship between D and E to F? Can I see any relationship? Well, what's the first obvious difference I see between these two? The 3 on the left and the 3 on the right. Yes, on the left, I had all 2s. On the right, they were all different. So what this tells me is we're going to find out that if my left and my right hand limits match, then that must also be the same thing for the two-handed limit. Yes. So in other words, they either all three of them match, they're the same number, or all three of them are different from each other. So you have either completely matching or none of them matching. If we really think about it, the one-handed limits on the left and the right, these are just more broad versions of the two-handed limit. It only works with one side. It's a little bit looser compared to the two-handed limit.
So like say A and B are the same, can you just assume that C will also be the same?
Yes, and that's actually what we're going to write in this next theorem. All right, so any other questions before I write this theorem?
So like C have D and E are different. If we get like how both of them are different, will the last one always be not exist or
It will be does not exist. Because the whole point of a two-handed limit is that everything's matching. Your left is meeting your right. So let's go ahead and put that into writing as a theorem. So this theorem is going to be one line. I'm going to say the limit as x approaches c from the left is equal to the limit as x approaches a number c from the right. Let's just say they're equal to L for some number. So if the left and the right are equal, then I'm going to draw an arrow pointing forward. My two-handed limit is also the same number, is equal to L. So if I have this, oops, let me extend that a little bit. This implies this here. In other words, if you know the left and the right, you should be able to automatically tell me what's the two-sided limit with zero calculation work. Because like we said, they either all match or they're different, and my answer is undefined. Well, it does not exist, to be exact. The other part of my question is, does this work in the reverse direction? If my two-handed limit is L or some number, does that mean that these other two, the left and right, have to be the same number as well?
Yes.
Yes, why so?
Because if L requires both of them to be equal, the left side to be the same number as the right side, then those two have to also, since they're equal, they have to be the same.
Yeah, and part of it is the two-handed limit. It's in the definition. The definition of the two-handed limit quite literally says we want to approach the same thing from the left and the right. So that means if you know the left and the right, you know the two-handed limit. If you have a defined two-handed limit, you know the left and the right as well. So if this was 4, then you know that these are also 4. The only other scenario is if this is undefined, all you know that these two are different from each other. All right, so this is going to be one of our theorems. And you're going to see problems in the future where I just say, here's the left, here's the right, give me the two-handed limit. And then that's something I expect y'all to be able to give me essentially instantly. It's either the same number or it's going to be does not exist, depending on what the left and right are. All right, so we have this expression. Let me pull up one thing just to make sure about something. All right, so from our example, we now know how to evaluate a limit from the left or from the right using the graph. What was the thing that we did after evaluating with a graph? Well, we worked on what if I just have an equation? What if I have like the limit of x squared as x approaches, I don't know, 1 from the left, the right, so on and so on. So what I'm saying here is that we're used to seeing this already. Limit as x approaches, I don't know, 7 of x plus 3. Quick review, what's the solution for this? 10, because I can quite literally just plug in 7 plus 3 and I get 10. My question now will be, does anything change if I did this?
No, it would still be 10.
No, if it's coming from the left, it would make it right.
It's still 10.
7 to the left.
So move
It'll be 10 to the right, and then
So I'm getting a couple of different answers.
are we saying that x approaches 7 from both sides, and that first one is true in this case?
Is that because it's the two-handed limit, so we already know that the left and right is the same?
Yeah, we know the two-handed limit. If we know the two-handed limit, we know the left and right already. So we just applied our theorem. This must be 10. In fact, if I change this to 7 with a minus superscript, nothing would change as well. So in other words, in terms of evaluating a limit of a function expression, even if it's a one-sided limit for left, right, or two-sided, my method does not change at all. I'm going to try to plug in my value. If it works, then we don't have a problem. So that's why I'm not really going to do too much of a focus on this part, in class at least, because it would just be regurgitating what we've already done. So now, why do I want to introduce these one-sided limits, and what use do they have for me? Well, remember that we did a couple of limits where I tried to plug in a number and I got 0 over 0. We could do some manipulations. Everyone was happy. Well, I was happy at least that we can solve it. But what if I ended up with something like this? The limit as x to approach, let's say 3, of, let's say 4 over x minus 3. My first issue, I can't just plug in 3. If I try to plug in 3, I get 4 divided by 0. I think we can see that. Furthermore, I didn't get 0 over 0, so I probably can't simplify this or manipulate it any type of way. So now I'm left with the question, what can I even do here? So what we're going to do is, let's try to find the left-hand limit at least. Because I know if I can get the left and the right, I know what the two-handed limit is. So let's start off with trying to find the left. I'm going to be a little bit lazy and copy and paste this, so I don't have to copy this 3 times. So let's try getting the left and the right. Again, if I know what the left and right are, I should be able to infer the two-handed limit. Because again, they either all match or they're all different. All right, so let's start with the left. Let's recall what this notation means. X approaching 3 from the left. Give me a number to the left of 3. 2. Give me a number that's even closer. Go even closer. We can go 2.9. Give me another one. 299. 2.9 over and over. We can keep on getting closer and closer. Because we know if I have one number, I can find another number that's even closer. So let's think about that. What happens if I plug in 2.9, for example, into my expression? So I'm going to go ahead and actually pull out a calculator and see what happens whenever I put 2.9. This is not something that you have to write right now. If you don't have a calculator, that's fine. This one's just to prove a point. So what happens whenever I plug in 2.9? So again, don't write this. 2.9, I get negative 40. What if I plug in 2.99? Someone plug that in for me. 400 are positive or negative? What about 2.999? What do you think is going to happen if I keep on adding nines? Yes, it's going to keep on adding more and more zeros. So if I keep on getting closer to 3 from the left, I keep on adding more zeros to this value. So what do you think I'm going to say my limit is going to be from the left if it keeps on getting larger and larger in the negative direction? It's definitely going to be negative. Do we have an expression to say something that's negative? Well, not just negative, but something that keeps on getting larger and larger. In other words, we can't really, what was that? Yeah, infinite, that is infinity. So I'm going to say for sure it's negative. I'm going to claim that this limit goes off to negative infinity. In other words, the closer I get to 3, the bigger my result becomes. We saw that. 2.9, I got negative 40. Get a little closer, I'm at negative 400. Touch closer, negative 4,000. You can imagine if I kept on getting closer and closer, I'd eventually end up with like negative 4 million, negative 4 trillion, negative 4 times 10 to however many zeros. So in other words, this limit is not approaching a single number. It just keeps on growing in the negative direction the closer I get. So this limit is what I'm going to claim to be equal to negative infinity. It doesn't end no matter how close I get. Let's go ahead and check the right. Give me a number to the right of 3. Yeah, we can do 3.1. If I want to be a little bit closer, 3.01. A little bit closer, 3.001. So I could do 3.1, 3.01, 3.001, 3.301. What do you think is going to happen whenever I plug these in? 40, 400, 4,000, 40,000. What do you think is going to happen as I continue to get closer to 3 from the right? It keeps increasing, and it never stops. What does that mean for my limit, do you think? Yes, positive infinity. So even though it's a little bit of a weirder answer, what does this mean for my two-handed limit? It does not exist. Why not? The sides do not agree. It does not exist. Because one is a positive infinity, the other one's a negative infinity. Remember I said if I want my two-handed limit to exist, my left and right had to be exactly the same. I don't care that they both have infinity. They're not exactly the same. One's positive, one's negative. So I want to take a quick note of this as well. Whenever we evaluate a limit, if I can plug in a number and get a real answer, that's perfect situation. No work for us to really do, maybe clean it up a little. If I try to plug something in and I get 0 over 0, that tells me, maybe I can try to do some manipulations, cancel some stuff out, and clean it up. Here we had the scenario where I had a number divided by 0. I can't clean it up at all. The question is, what conclusion can I probably make about any time I get a number divided by 0? My left and right hand limit, they will be either positive or negative infinity. Not necessarily. Because, for example, I could have easily swapped this and said 3 minus x, and that would have gave me positive numbers. Or even simpler, I could have just put negative 4 on top. So the left doesn't always necessarily mean negative infinity, and the right doesn't always mean positive infinity. It could be either or. But that leaves the question,
Could they both possibly be like, say the right side was positive infinity and the left side was positive what would that be overall?
Yeah. So what would happen if we had the left was positive infinity, the right was positive infinity? What does that mean for our two-handed limit?
Wouldn't that mean there's a point in between the two that equal, that are like the same? Like if they're both positive infinity on either side, looks like that, which means there's a point in the graph where they both equal.
Not exactly like so. For example, we may have a graph. Well, let me answer one question first before I get to that. First question is, if they're both infinity, remember, either they all match or they're all different. If these two are both infinity, then my two-handed limit would also be infinity. But what does that look like in terms of a graph? Actually, if you were to graph this function, just so that we have a little bit of a visual, I'm going to draw it very quickly. It's not going to be very exact or to scale. Let's see. Here is 3. Check. That's good. It will look something like this. Say that this is 3. What happens whenever I'm approaching 3 from the left? It goes down further and further. From the right, it's going up further and further. If you remember from some old terms from algebra, this occurs when we have this imaginary line that we can't pass, that we called the asymptote. So now I want to go back to my previous question here. If I ever end up and try to plug in my value, and again, number divided by 0, I can't do any cleanup work. This is a red flag telling me my left and right hand limits. My only options are positive or negative infinity. Because I end up with the same scenario. I can't plug it in, I can't plug 3 in directly. I have to do something really close to the left or from the right. So again, if you ever end up with a number divided by 0, whenever you try to plug it in, my left and right hand limits, we expect them to be either positive infinity or negative infinity. Now the question is, do I really need to plug in 2.9, 2.99, 2.999 over and over again to see if it's positive or negative infinity? No, not really, because first off, if I'm at this point, I know it's either infinity or negative infinity. The question now is just, how do I know if it's positive or negative? Let's look at what we have here. If I look at the top, 4, is that positive or negative? Positive, right? 4 is obviously a positive number. On the bottom, if I take a number to the left of 3, so smaller than 3, and subtract 3, is that going to be positive or negative? Negative, because any number to the left smaller than 3, subtract 3, you get a negative. What happens whenever you do a positive on the top divided by a negative on the bottom? What's my final result? It's going to be negative. Positive divided by negative, we get a negative. Let's see if I can do that same analysis here. I can try to plug in 3. I get 4 divided by 0, red flag. I know my answer is infinity or negative infinity. The question now is, which one is it? We take a look at the top and the bottom. On the top, 4, again, positive. On the bottom, if I take a number bigger than 3 and subtract 3, do I get a positive or a negative number? Positive. Again, to the right of 3, you think 3.1, 4. If I subtract 3, then that's positive. What's a positive divided by a positive? That's still positive. So, since I know my only options are positive or negative infinity, my answer must be positive infinity. So we have this here. All right, so this is where we'll actually stop for today's material. I have someone that has to come in and just give a small little talk. If you want to go.
Hello everyone. Good afternoon. So my name is Obukomai Jaife. I'm from the Tutorial Assistance Network. That's the Freshman Academy. So I'm here today to just tell you about the Freshman Academy. We're there to help you if you need help with your classwork, if you need to discuss your assignments, anything to understand in class, you need to go through to study for test exams, we are there in the library, first floor. So you can schedule an appointment online by going to Navigate, or you can just basically drop in. You can meet me, I meet you, this is John, this is one of the tutors there. And a lot of other tutors there, so we are there to help you. And we want you to come because it's free, but there, you know, freshman year can be hard, math is can be hard at all. So basically, not just math, any course you need help with, we are always here to help you. So just stop by and feel us. So, thank you.
Thank you.
Yes. Thank you.
Thank you.
Not a problem. So as y'all saw, we do offer tutoring services on campus. There are some tutors that are specifically here to help for math classes, especially this class. Let me go ahead and finish this as well.